Hi everyone, this is John Mark, a lecturer at KCE College. I'll be taking you through quantitative analysis, and for today's session I want us to learn about the queuing theory. And then to start with the introduction and a queuing theory. Now queuing theory is just an analysis of the situation where a client arrives and joins a queue or a line in order to receive a service. So for example, have you ever queued either in a hospital, in a bank, Huduma Center, etc. So that's what we'll be analyzing for today's session. And we are saying that queuing analysis is the analysis of the situations in which a client or a customer arrives and joins a queue in order to receive a service. E.g., where they practice the queuing analysis in banks, in hospitals, also Huduma centers, also in garage, etc. So that's what we'll be looking at the queuing analysis. Then let's look at what are the assumptions of a single channel queuing system. Queuing system. So, under single queuing system, we are talking about the single channel queuing system. This is where you are receiving a service from one particular point. For example, if you go to the bank and then you found there is only one teller or there is only one queue need, you are getting service from one person. That's the single channel queuing system. And what are those assumptions? And the assumptions are the same as the characteristics or the disadvantages or the limitations. And one of the characteristics or one of the assumptions is that the calling population is unlimited. Number two, the queuing length is also unlimited. Then number three, the waiting line follows FIFO discipline. Then the arrival pattern is irregular and follows Poisson distribution. And then also the service time is also irregular or random and follows exponential distribution. And then number 6 is that the service rate denoted by mu is always greater than the service or the arrival rate. Arrival rate is denoted by lambda. Yeah, those are some of the assumptions of a single channel queuing system where the calling population is unlimited. When you talk about the calling population is unlimited, what we mean is that the number of the client who arrive, there is no restriction, provided the client arrives and receives the service. So that's why I'm saying that the calling population is unlimited. Then number 2 is that the queuing length is unlimited. That one also has no restriction. And then number 3 is that the waiting line follows FIFO discipline. And the FIFO discipline, that's basically first in, first out. And then number 4 is that the arrival pattern is irregular. Now the arrival pattern, this is what we mean. For example, if you're entering to a bank, in 1 minute, they can arrive, we can have 2 clients arriving. The other 5 minutes, we have 6 clients arriving. The other 10 minutes, we have 3 clients arriving. So that's why you're saying that the arrival pattern is irregular. they have not that consistent number or a fixed number of the client who arrives at a given period of time. Then the service time is irregular. When you talk about the service time, assuming we have client 1, client 2, and client 3, and all of them, they want a service from this specific teller. So in that case, the time taken to serve client number 1 will not be necessarily the same time taken to serve client number 2, and will also be not the same time taken to serve client 3. For example, client 1 may take like 5 minutes. Client 2 takes 8 minutes. But client 3 may even take 20 minutes. That's why you are saying that the service time is irregular or it's random. And then the service rate is greater than the arrival rate. So we are saying that U and lambda, so where U is the service rate, this one should represent service rate per hour, and this lambda means the arrival rate per hour. And you see, both the service rate and the arrival rate, in this case, they should be expressed per hour. So that we are saying that the service rate is always greater than the arrival rate. That means the rate at which they are serving the client should be greater than how the rate of the client they are arriving. So those are some of the assumptions under a single channel queuing system. And if the examiner asks you about the characteristic or the limitation of the single channel queuing system, you still include the same. So that's the assumption. So now I want us to look at something else. Queuing analysis. And for the queuing analysis, we'll be evaluating various analysis there. Number 1, it's probability. Probability of being busy. It's also called utilization factor, or what we call traffic intensity. Traffic intensity. Yeah. So how do we get probability of being busy? For example, what's the probability if you go to the bank, you found that the teller is busy? So probability of being busy, you take arrival rate, you divide by the service rate. And number 2, it's all about probability of being idle. How do we get probability of being idle? Now, if this is the probability of being busy, that means probability of being idle, you'll take 1 minus probability of being busy. That's the arrival rate over the service rate. That's how you get the probability of being idle. Number 3, probability. What's the probability of having more than n items? For example, what's the probability if I go to the bank, I'll find more than 10 clients. So that 10 will be presented by n. So probability of having more than n item. So this is having more than n item. This is how you get it. You take a lambda, you divide by the service rate raised to power n plus 1. So that's how you get the probability of having more than n items. You take arrival rate, arrival rate, you divide by the service rate, in bracket, raised to power n plus 1. Number 4, probability of having exactly n items. So for example, in this case, we can say, what's the probability of getting 10 clients in a bank? So in this case, we are talking about exactly n items. So how do we get probability of having n items? You take lambda, you divide by u, raised to power n, you multiply by 1 minus lambda raised to power u. So that's how you get the probability of having exactly n items. Number 5, waiting time. How do we get waiting time in the system or waiting time in the service? It's denoted by WS, and the waiting time in the service or the system, you take 1 minus the service rate minus arrival rate. Number 6, waiting time. How do we get waiting time in the line or waiting time in the queue, denoted by WQ? So and this is how we get the waiting time in the queue. Waiting time in the queue, you take lambda, you divide by U minus lambda. So that's how we get that. And then number 7, how do we get items in the system, denoted by LS? Now, when we talk about the item, you have to differentiate between, we have the waiting time and we have the item in the system. Now, the item in the system, for example, if you go to the bank, the item are the current waiting. If you go to the garage, the item are the number of cars. So in this case, it's the item in the system. So when you talk about the item in the system, for example, if you go to the bank, item in the system comprise of the number of the current, both in the queuing and the one being serviced. So in that case, you take item in the service, you take a lambda, U minus lambda. And lastly, number 8 is how do we get the number of items in the queue or item in the line? So that means how many number of the currents are there in the queuing? In the queuing, not in the queuing system. When we talk about the queuing system, we are talking about the system. In this case, the number of items in the queue. How many people are there waiting to be served? So in that case, the item in the queue is the same as the item as the waiting time in the queue, where item in the queue denoted by LQ, the formula is the same as for the waiting in the queue. You take lambda, U minus lambda. The only difference between the waiting time in the queue and the item in the queue is that for the item, you square the numerator lambda there. So that's how you get. So that's the analysis. And kindly, this one you have to get them at your fingertips. And then you need to interpret them when you talk about the item and when you talk about the time. And then you have to differentiate when the examiner asks about the system and also the queue. When the examiner, sometimes the examiner may ask the item or the waiting time in the queuing system. Queuing system. Now, when you talk about the queuing system, you need to ask yourself, is the examiner asking about the system or the queue? When you talk about the queuing system, we are talking about system. So, for example, item in the queuing system is the same as the item in the system. Yeah, good. So now with that, I want us I can give you an illustration. So now, I don't want to wrap that. So, assuming a certain bank, has a service rate of 30 currents per hour. So this is 30 currents per hour. And the arrival rate of the current, assume is 25. Like that. So we just assume that, that the service rate per hour is 30 and the arrival rate is 20. Now we need to answer the following questions. Now, and the first question is that, what's the probability of being busy? Probability of being busy. So probability of being busy, we have said that in this case you take arrival rate, you divide by the service rate. So in this case you take arrival rate is 25, you divide by the service rate, which is 30. Like that. And with that, so how much do you get? And then the second one, it will be probability of being idle. So in this case, you take 1 minus the arrival rate, which is 25. You divide by the service rate, which is 30. And you get that. Probability of having more than n items. So in this case, I need to be specific. What's the probability of having more than 5 items or more than 5 crowns? So in that case, it will be lambda, which is 25. You divide by the service rate, which is 30, raised to power, you say it's n plus 1. So it will be 5 plus 1. and then you get your probability there. So what about probability of having exactly n item? So in this case, I need to be specific. Probability of having 10 clients. Let's just be specific like that. Probability of having 10 clients. So in that case, you take their arrival rate, which is 25. You divide by 30, raised to power n. In this case, our n is 10. And then you multiply by 1 minus, in short, this is the probability of being idle. 1 minus 25, you divide by 30. After now, you have the formula. It's all about getting the service rate and the arrival rate. And then you apply them to the formulas. Then, waiting time in the system or the waiting time in the service. So in that case, how do we get that? The waiting time in the system, you take 1, you divide by, our yield was 30, minus 25. And you'll have 1 over 5. 1 over 5 is the same as 0.2 hours. Or you can show in minutes. You just multiply by 60. At 20% of 60 is 12 minutes. So you can either show in hours or you can show in minutes. Waiting time in the line or waiting time in the queue. For how long if the service rate is 30 and the arrival rate is 25, for how long will you wait in the queue before you are being served? So in that case, you take the arrival, which is 25, you divide by service rate, which is 30, into bracket 30 minus 25, like that. So that times 5 is 150, 25 over 150, and that you get that. Then you can put it in hours or you can show it in minutes. And then items in the system. So how can I determine the number of the client waiting in the system, or in short, is the number of the client in the waiting hall? So in that case, you take the lambda, which is 25, you divide by the service rate, which was 30, minus 25, and you'll have it's 5. And then items in the queue. How do we get items in the queue? Now, the item in the queue is the number of the client waiting to be served. So in that case, you take lambda, which is 25, you square, divide by 30 minus 25. So that's how you get that. So now we do now questions from the past paper. You can do the questions from the past paper. And I want us we start do the question from the past paper. We can start with the one for November 2019. November 2019, question 2D. Hoping we are there. And you are told that a bank teller can open new account at an average rate of 3 accounts per hour. Customer requiring to open an account arrives at an average of 2 customers per hour. The management of the bank has established a single channel, single phase queuing system required. So now, before we answer those questions, one thing, you need to identify the service rate per hour, and then you need to get the arrival rate. Let me read again. A bank teller can open a new account at an average rate of 3 accounts per hour. So you ask yourself, if this teller can open an account of 3 accounts per hour, that means that's the service rate. That means you can serve 3 clients per hour. Then you are told that customers requiring to open an account arrives at an average of 2 customers per hour. So the arrival rate of the client is 2. And remember, one of the assumptions was that the service rate should always be greater than the arrival rate. Now let's go to the required. Required number 1. Number 1, it's the average number of customer in the system. The average number of customer in the system. So you need to ask yourself, they have asked about the number of the customer. So if they ask about the number, they're asking about the item. And then it's the average number of customers in the system. So that means it's the items in the system. And how do we get the items in the system? It's Rabda U minus Rabda. So it will be, our Rabda here is 2. You divide by the service rate, which is 3, minus arrival rate, which is 2. So in that case, and you have is 2. So the item in the system, there are 2 customers. Good. Number 2 of the question. Number 2, you're told that the average time spent by the customer in the system. The average time spent in the system. So if they talk about the time, that means is the waiting time in the system. Because they are saying that. The average time spent by a customer in the system. So it's the waiting time in the system, and it's 1 U minus Rabda. So it's all about the formula, right? So it's 1, you divide by the service rate is 3 minus 2. So in that case, it will be 1 hour, or you can show it as 60 minutes. Because 1 hour is equal to 60 minutes. Let's go to number 3 of the question. Number 3, the average number of customers in the queue. The average number of the customers in the queue. After, if they talk about the number, so they're asking about the items in the queue. And how do we get the item in the queue? It's Rabda square U minus Rabda. So it will be our Rabda, which the arrival rate was 2. It's 2 square. You divide by the service rate, which is 3 minus 2, like that. So that's 4. 4 you divide by 3. So it's approximately 1.22, eh? Let me say that. Yeah, it's 1.33, eh? Which is equivalent to 1. See, in this case, we are talking about the number of the customer. You can't say 1.33 customer. So it's equivalent to 1 customer. And lastly, number 4. Number 4, the required for number 4 was the utilization factor of the service utility. Utilization factor. And we say that utilization factor is the same as the probability of being busy or the traffic intensity. So that one is all about probability of being busy. Utilization factor. And how do you get the probability of being busy? We said it's Rabda over U. So in like that. So you'll take our Rabda there, it is 2, you divide by 3. So in short, it will be 0.667. So that's the probability of being busy. So that's what the examiner wanted. Eh? Okay, let me add another one. What's the probability of being idle? Probability of being idle? In case the examiner asks about the probability of being idle, you ask yourself, if the probability of being busy is 0.667, what about the probability of being idle? So you just take 1 minus 0.667. That means the probability of being idle, it's 0.333. Or use the formula. Probability of being idle, we said it's 1 minus Rabda over mu, like that. So it will be 1 minus the arrival rate, which is 2, over the service rate, which is 3. And you still have 0.33. Like that. So you can look at that. And then we can try another illustration. Okay, through that, open May 2016. May 2016, question number 2A. Sorry, question 3D. Question 3D. May 2016, question 3D. So let me read the question. And we are told that a cashier at a departmental store can serve on average of 24 customers per hour. So the service rate can serve an average of 24 customers per hour. The arrival rate of the customer averages to 20 customers per hour. That's the arrival rate of the customer averages to 20 customers per hour. That means our arrival rate is 20. The departmental store applies a single channel queuing system. Required, number 1. The probability that the cashier is idle. So number 1 is the probability of being idle. So in that case, first of all, you have said that you identify the service rate and the arrival rate. With that, now we can get the probability. How do we get the probability of being idle? It's 1 minus lambda over u. So it will be 1 minus the arrival rate, which is 20, you divide by 24. And you get probability of being idle. It will be 0.1667. That is it. Now we can go to number 2. Number 2 of the question is that the average number of the customers in the queuing system. The average number of the customer in the queuing system. So that's all about item in the system. They are talking about the queuing system. So that's the number of items in the system. So in this case, it's lambda u minus lambda. So it will be, our lambda here is 20 divided by the service rate, which is 24, minus the arrival rate, which was 20. And the item in the system, you have, it's 5. Yeah, it's 20 divided by 4, you'll get 5. So you have 5 customers. Then number 3 of the question. Number 3 of the question was, the average time a customer spends in the queue waiting to be served. The average time customers spend in the queue waiting to be served. So they're asking about what? They're asking about the time. So it's all about waiting time in the queue. Because they're asking about the average time a customer spend in the queue waiting to be served. So they're asking the time when you're waiting in the queue. So in that case, how do we get the waiting time in the queue? It's lambda u minus lambda. So in that case, you'll have our lambda here was 20 divided by 24 minus 20. In that case, you'll have that waiting time in the queue. It's 0.21 hours, or you can convert it into minutes. You can multiply by 60 minutes. So that means on average is 12.5 minutes. So that means after the customer, when the customer arrives, it takes an average of 12.5 minutes before you receive a service or before you get to the service station. So that's what it means. So, and that's all about that question. So we can still try another question. Let's do September 2015. Let's do September 2015, question 2A. September 2015, question 2A. So we are told that the city theater has 4 auditorium, namely C1, C2, C3, and C4. And each auditorium perform a different play at any given time. The performance starts at different time to avoid long queues that would occur if all auditorium were to start performance at the same time. The theater has a single ticket booth, so that means if it has a single ticket booth, that means it's a single channel. The theater has a single ticket booth, and the cashier, who can maintain an average service rate of 280 patrons per hour. Cashier can maintain a service rate of 280 patrons per hour. The arrivals are poison distributed at an average of 210 patrons per hour. Let me repeat that sentence again. The arrivals are poison distributed at an average of 210 patrons per hour. So that means our arrival rate is 210 per hour. The service are assumed to follow an exponential distribution. Yeah, those are the things we discussed when I was giving you about the assumptions. Required, number one, the average number of patrons waiting in line to purchase the ticket. Can you think about that? The average number of patrons waiting in line to purchase the ticket. It's asking about what? So number 1 is the number of the patron. So in that case, that means we are talking about the item, and then they are talking about the patron waiting to purchase the ticket. So when you are waiting, that means is the item in the queue. They are waiting in the queue. So how do we get the item in the queue? Waiting in the queue, it's lambda square divided by u minus lambda. So our lambda here in this case is 210. 210 squared, you divide by our service rate or our mu, which is 280. 280 minus 210. That's how you get the items in the queue. And your items in the queue be approximately 2.25, which is equivalent to 2. Then number 2 of the question. The average time, number 2, the average time spent waiting in line to get to the ticket window. The average time waiting in the queue to get, spent waiting in line to get to the ticket window. So that means is the waiting time in the queue. The time you are waiting to get to the ticket window. It's all about waiting time in the queue. And in this case, how do you get the waiting time in the queue? We say that waiting time in the queue and the items in the queue, the formula is the same. The only difference is that for the items, you don't square the numerator here. So it will just be like that. So our arrival rate is 210. We divide by 280. 280 minus 210. Like that. I'll have that. I found that your waiting in the queue will be 0.011 hours. And then you can convert it to minutes. You divide by 60 minutes. In that case, you have 0.64 minutes. Number 3 of the question. Number three. The average time a patron spend in the system. Average time a patron spend in the system. So that's the waiting time in the system, which is 1 u minus lambda. So in that case, you'll take 1 divided by our service rate is 280 minus 210. So that's 1 over 70. 1 over 70, and that one you get it's 0.014 hours, or you can convert them into minutes. You multiply by 60 and you have 0.86 minutes. Let's go to number 4. Number 4, the question was the percentage of time the cashier is busy. So how do we get probability of being busy? Probability of being busy, you take lambda, you divide by u. So our lambda here is 210. You divide by mu, which was 280. But in this case, the examiner wants the probability of being busy. So you multiply by 100. And that one will have it's 75%. That's 75%. Let's go. Lastly, number 5. Number 5, you asked that. Number 5. The probability that there are more than 2 people in the system. Probability that there are more than 2 people in the system. More than 2 people, you're talking about probability of having more than n items. And how do you get that? We said it's lambda. You divide by u raised to power n plus 1. So it will be, our arrival rate is 210. You divide by 280 raised to power n plus 1. In this case, we are told that probability of having more than 2 people. So it will be 2 plus 1. So you take 210 divided by 280, you get 0.75. Then cubed or raised to power 3. And in that case, we will have probability at 0.422. 422. Like that. Hoping the progress is good. Can still try another question. So you can look at that so that we look at another question. After you're through with that, you can open May 2015. May 2015. Question 2C. May 2015. Question 2C. And we are told that A bank has one counter to serve customers who have complaints about their loans. An average of 96 customers arrives at the counter in an 8-hour day. The customer service at the counter spend irregular amount of time servicing the arrival, which has been found to have an exponential distribution. The average service time per customer is 4 minutes required. Now, before you go to the required, number one, you have to identify the service rate, and then you have to identify the arrival rate. And then let me repeat something else. We say that the service rate and the arrival rate should be always expressed per hour. So, in that case, we are told that an average of 96 customers arrives. So, that's all about the arrival rate. So, that means arrival rate, an average of 96 customers arrives at the counter in an 8-hour day. So, that means 96, they arrived in an 8-hour day. So, that means the arrival rate per day in an 8-hour day. So, to get per day, per hour, you just divide by 8. So, that means the arrival rate per hour was 12. Then we are also told that, that's the last sentence. The average service time, that's all about the service. The average service time per customer is 4 minutes. So, how can we get this, the service rate? That the average service time per customer is 4 minutes. And we said this should be per hour. This is how you argue. If one customer is being served for 4 minutes, what about in 1 hour, which has 60 minutes? If one customer is being serviced for 4 minutes, what about in 1 hour? 60 minutes will have already served how many customers? So, I will get your service rate, it's 50. So, just take 60 divided by 4. So, that's the first step. If you fail on the first step, that means all the other what is required, you will get a wrong answer. So, kindly be very keen when you're getting the service rate and the arrival rate. And then you need to express them per hour. So, now we can go to the required number one. Required number one. The average number of the customer in the system. Average number of the customer in the system. That's about the item in the system. And the item in the system is Rabda, U minus Rabda. So our Rabda will be 12. Divided by 15 minus 12. And you have that. So on this one you have its form. Number two. The average number of the customer waiting to be served. Average number of the customer waiting to be served. If they are waiting to be served, that means they're in the queue. So it's the item in the queue. And how do you get the item in the queue? It's Rabda square, U minus Rabda. So in that case, you'll have your Rabda in this case is 12 square divided by the service rate is 15 minus 12, like that. So on the item in the queue, you have it's an average of 3.2, which is approximately 3. Number 3, required number 3. The average time a customer spend in the system. Now that's the waiting time in the system. The waiting time in the system, it's 1, U minus Rabda. So it's 1. Service rate here 15 minus 12. So that's that. If you get that, that's 0.33 hours. You can multiply by 60 to get in minutes, and that is 20 minutes. Yeah. So that's the waiting time in the system. Number 4. The average queue waiting time. Average queue waiting time. That's the waiting time in the queue. It is Rabda, U minus Rabda. So our Rabda there is 12 divided by 15 minus 12. With that waiting time in the queue, it will be 26667 hours. Then you multiply by 60 to get them in minutes. So it will be approximately 16 minutes. So now let me explain something here. Waiting time in the system, waiting time in the queue. Now we say that waiting time in the system is the time waiting. Now let's assume this is the door for the bank. That's the door. And then you queue, and then you get to the service, and you are being served here. Now the time you are exiting. Now the waiting time in the system is a time between you entering to the bank and until upon completion of the service. That's what we call waiting time in the system. That means from the time you enter to the bank, you spend 20 minutes in that bank from the queuing and getting the service. And in this case, waiting time in the queue. For how long did you take waiting in the queue for you to get to the service booth? In that case, you took 16 minutes. So in short, for how long did you go to the service? You are serviced for only 4 minutes. So that's what it means. Number five, we are told that the probability that the customer will receive immediate service upon arrival. The probability that the customer will receive immediate service upon arrival. So if you are the customer and you enter to the bank and you receive immediate service upon arrival, what is the examiner asking in this case? You go to the bank and the teller tells you, welcome, welcome. You receive immediate service. That means the teller, they were idle. So in short, they're asking probability of being idle, which is 1 minus lambda over u. So it will be 1 minus your service rate is 12 over 15. And the probability of being idle was an amount of 0.2. Yeah, that's the probability of being idle. You cannot argue with the probability of being busy. Because if you are being busy, you'll have to queue. But in this case, if you are receiving immediate service upon arrival, that means the cashier or the teller, they were idle. And lastly, number 6, the probability that the number of customers in the system is greater than 3. Is greater than 3. That's probability of having more than n item, which is lambda over u n plus 1. So it will be, our service rate there is 12. You divide by 15. We are told that more than 3, they are more than 3. So it's 3 plus 1. And you get that. So, and the probability of having more than 3 customers will be 0.41. So on that, I want you and go and try the following assignments. You can try June 2010. June 2010 question 5A. Also you can try December 2010. December 2010 question 4C. Question 4C. So now I want us to look at another part of stating the queuing analysis. Now under the queuing analysis, now we want us to analyze the cost associated with queuing. Now when you talk about the cost associated with the queuing, we have 2 classifications of the cost when it comes to queuing. And I want to illustrate them here. The cost associated with queuing, or the queuing cost. So let's look at the cost associated with queuing. And they are usually classified into 2. One, we have the service cost, and number 2, we have the queuing cost. Let me explain the two. So when you talk about the service cost, now the service cost is the cost which will be incurred by the service provider in order to minimize the time of the client waiting in the queue. So the service cost is the cost which will be borne by the service provider. Then we have the queuing cost. Now the queuing cost is the cost which will be incurred by the client as a result of waiting. Now that's what we call the opportunity cost, or what we call the lost goodwill. So we are saying that, now let's write something here, that the service cost is the cost incurred by the service provider, in order to minimize the queue waiting cost. So for example, if you go to the bank, You may find that the bank, they may add more tellers so that they can serve you faster. You see, if you hire another teller or an extra teller, that means your cost is going up. Nowadays, also, they are having what we call the free Wi-Fi. You see, free Wi-Fi, so that as the client is waiting there, provided there is Wi-Fi, mostly for the young generation, they don't mind waiting, provided there's free Wi-Fi. So that is part of the service cost, the cost which will be incurred by the service provider. Then we have the queuing cost. Now, the queuing cost is the cost incurred by the client or the customer as a result of waiting. That is, it's known as lost goodwill or opportunity cost. Opportunity cost. What do we mean? Now, assuming you are a business person, owning a shop, you have a shop somewhere, and then you decided to close the shop for only 30 minutes so that you can get a service from the bank. You rushed to the bank. Now, assume this is your shop, per hour you usually make 1,000 per hour. Assuming from this shop you usually have an income of 1,000. And then decided to rush for the shop, to the bank to get a service. And then, upon the arrival to the bank, you found that there was a system failure. And that means you spent 2 hours waiting to get a service in that bank. So now, these 2 hours, remember you had already closed your shop, and your shop generates 1,000 per hour. So that means, if you waited for the bank, for the system to reboot again, for 2 hours, that means you waited for 2 hours. Assuming these 2 hours you are still in your shop, you could have made a profit of 1,000 per hour times 1,000. That means for 2 hours, you have lost 2,000. Now, this is what we call opportunity cost. Opportunity cost, or what we call not the queuing cost, sorry. This was not the queuing cost. It was supposed to be waiting cost, sorry. Waiting cost. Yeah, the waiting cost, is the opportunity cost or the waiting cost, the cost which will be incurred by the service, by the client as a result of waiting. And this is how we determine the amount, the waiting cost. Waiting cost, this is how you get it. You take relevant duration, you multiply by the relevant waiting time, and then you multiply by the arrival rate, you multiply by the opportunity cost. Opportunity cost. That's how you determine the waiting cost. The relevant duration times the relevant waiting time, you multiply by the arrival rate, you multiply by the opportunity cost. Now, for the relevant duration, this is the number of hours which that business operates. Now, for example, in a bank, they usually mostly operate in 8 hours. So the 8 hours is your relevant duration. Now, relevant waiting time, it can either be waiting time in the system or waiting time in the queue. So your relevant waiting time, based on the formulation of the question, you need to differentiate. Are they asking about, or what time do you mind mostly? Is it waiting in the system or waiting in the queue? Now, for example, if you go to the bank and you found there is a queue, there are like 15 people ahead of you. So in that bank, what you mind most, it's not about the time in the system, it's all about the time taken for you to wait in the line, waiting in the queue. So if that is the case, that's what you mind mostly when you go to the bank. That one becomes your relevant waiting time, the waiting time in the queue. And then the arrival rate, that one is direct, and then opportunity cost. Good. So having that in mind, you need to get this formula and then the two classification of the cost so that we can do an illustration. So with that, I want us, we try an illustration. And the first question I want us to do, let's do December 2017. December 2017, question 4A. In a certain business facility, the mean arrival rate of client is 800 clients per hour. The mean arrival rate, it's 800 clients per hour. The mean service rate is 820 crunch per hour. The mean service rate, the service rate is 820. Remember I said that the service rate should always be greater than the arrival rate. The facility operates between 6 a.m. and 6 p.m. every day. So if they're operating between 6 a.m. to 6 p.m., that means the relevant duration they're operating for 12 hours each day. The management of the facility are concerned about the average number of customers in the queuing system. Let me repeat again. The management of the facility are concerned about the average number of customers in the queuing system. That means our relevant waiting duration or waiting time is the waiting in the system. Because we are told that the management is concerned about the average number of the customer in the queuing system and wish to improve the facility in order to serve an average of 847 crunch per hour. They are proposing to upgrade so that the service rate they can serve 847. They improve the facility to serve 847 instead of 820. The cost of improving the facility amounts to 18,500 per day. Now that cost of improving the facility is what we call the service cost. The cost which will be incurred by the service provider. Each hour lost cost the facility 125 shillings. So if each hour lost is cost the facility 125, that's what we call the opportunity cost. Required, number one. The average waiting cost per day. Average waiting cost per day. How do we get that? So you have said that waiting cost, you take the relevant duration, you multiply by the relevant waiting time, you multiply by the arrival rate, and then you multiply by the opportunity cost. In this case, our relevant duration, we are told that the bank operates between 6 a.m. and 6 p.m. That means the relevant duration, they are operating for 12 hours per day times the relevant waiting time. We say that relevant waiting time can either be waiting in the system or waiting in the queue. But based on our question, they are minding about the number of the current in the waiting in the system. So that means our relevant waiting time is the waiting in the system. And how do we get the waiting in the system? It's 1 mu minus lambda. So it will be 1. Our service rate here was 820 minus the arrival rate, which is 800. So that's 1 divided by 20, and 1 divided by 20, you found it's an amount of 0.05. It's 0.05. So it's the relevant duration, which is 12, times relevant waiting time, which is 0.05, times the arrival rate, and our arrival rate was, this was the arrival rate. Arrival rate does not change, which is 800, and then you multiply by the opportunity cost. Remember, you are told that each hour lost cost the facility 125 shillings times 125, like that. So that's how you get the waiting cost. 12 times 0.05 times 800 times 125, and you have it's 60,000, and you get your 4 marks. So that was number 1. Let's go to number 2. That was number 1. Number 2 of the question. Number 2. Number 2, I told that advise the management on whether they should improve the facility. 4 marks. You advise on whether to improve. Now, when you're advising, before you make an advice, how do you advise them? So number 1, you have to compare the cost before the improvement and after the improvement. Now, after the improvement, so now let's look at the cost of improving the facility. If we improve the facility, there is something which will change. In this case, our waiting in the system will change, which is 1 u minus lambda. So it will be 1. Our service rate, we are told that after we improve the system, we improve the facility, we will not be serving 820. But now in this case, our service rate will increase to 847. So that means, this 847, that means the service rate in this case will be 847 minus, lambda does not change. The arrival rate still will remain as 800. So in that case, you'll have it's 0.02. So now let's get the waiting cost. Now the waiting cost, relevant duration does not change. The bank will still be operating for 12 hours per day. And then the relevant waiting time, that's what has changed. From 0.05 to 0.02, 0.02 times, arrival rate does not change. Arrival rate remains to be 800 times the opportunity cost was 125. And in that case, how much will you get? So you'll have 24,000. That's the waiting cost after the improvement. But there is another cost. There is a service cost. Remember we were told that, We were told that. The cost of improving the facility will amount to 18,500. After we improve, we'll have to improve that system at 18,500 per day. So that means the total cost, you take the waiting cost, you add the service cost of 18,500. And in total, you'll have an amount of 42,500. Now you ask yourself, you are told that advise the management on whether to improve. Now, before the improvement, you see the total cost was 60,000. But after improvement, the cost has gone down to 42,500. That means the management should improve the facility, because in this case, we have cost savings. Good. You have another 4 marks. So let's go. Rastri number 3, we are told that. Number 3, we are told that. Compare the probabilities that the total number of the clients in the queue and those being served is greater than 17 in the existing and improved facility. In the existing and the improved facility. You compare the probability of those clients in the queue and those being served. They are greater than 17. So in short, the exam is asking about probability of having more than n. In this case, more than 17. So we compare between the existing and improved. Under the existing, how do we get probability of having more than n item? We said it's lambda over u n plus 1. So it will be our lambda or arrival rate does not change, was 800. You divide by the service rate. Before the existing, the service rate was 820. N plus 1. We are told that they are greater than 17. So it's 17 plus 1. You get that probability. For the improved system, the formula is the same. The arrival rate does not change. It's 800. But now what changes is our service rate. On the improved system, the service rate is not 820, it was increasing to 847. Raised to power n plus 1, more than 17, so it's still 17 plus 1. So I found that the probability here, it's 0.64. But when we improve the facility, the probability of having more than 17 in the same system will reduce to 0.36. The more number of people we serve, we reduce the number of the people in the queuing system. That's why the probability have reduced. Good. So that's the end of that question, and you get your 12 marks. As simple as that. So I want you to go and try the following assignment. You can try November 2015. November 2015, question 4C. Also, you can try May 2014. May 2014, question 3A, and also you can also try June 2013, question 1B. And then from the handout, you'll get the notes. From the handout, I have done another extra question on the queuing cost. So you can review that question, try to go through it, and then you do this, you follow what we have done. From the notes, you can be able to follow that, and then you try the one I have already tried in the notes, in that handout, and then you can try the following. So that was our topic today, the queuing analysis, and this is a topic which mostly it never misses in each an exam. So keep on revising and make sure kindly try to do those assignments. After you do your assignment, then kindly scan them and then you share them to me. And this is my contact. We have said that you scan using a CAM scanner as one document. After you scan, you save under magic color. And then from there, you share it to me via WhatsApp. And this is my contact. Yeah. I'm John Mark. Thank you.